Can you guys see the screen?
Yes. So Fai, I'll warn you in 25 minutes or so, okay?
Sure. Yeah, thank you. First of all, I would like to thank the organizer for inviting me for this exciting workshop. And I hope the screen displays is okay, right? It's in the presentation mode.
It is.
Okay.
Yes.
Okay, and today I'll be talking about stripe phases and a little bit about a compressibility measurement of this charge order states. And I call it a charge order enhanced compressibility. And you'll see in a moment my argument. And it's usually interpreted as a negative compressibility of the sample, but that's actually not what we think for the interpretation. Okay. Oh, how do I advance? Okay, but before going, I would like to, acknowledge the people involved in this work. The stripe phases I'll be talking about is led by Chenhao Jin, Zui Tao, and Tingxin Li. And the compressibility work I'll be talking about is led by Tingxin Li and Raymond Zhu. And we also acknowledge theoretical support from Wei Elsa at Cornell and Liang Fu from MIT. And also, we are very grateful to have the excellent crystals from TMD crystals from the Columbia group, from Jim Hong's group, as well as the HBN crystals from the Japanese group. Okay, first of all, a very general introduction for stripe phases. They are just phases that spontaneously break the rotational symmetry of a material, right? And they can be classified into a few, stripe phases usually can mean a few different things. It can be a stripe crystal. In this case, in addition to the broken rotational symmetry, it also breaks the translational symmetry of the system. In a 2D case, that would be breaking the translational symmetry in both directions. There's also the smectic phase, which is pretty close to it's somewhere in between the nematic phase and the crystal phase. It breaks rotation and also breaks translation in one direction. And finally, we have the nematic phase, which only breaks the rotational symmetry, but preserve the translational symmetry of the system. Okay. Well, stripe phases are important. They have been observed in quantum Hall system. For instance, for the new bigger than 1 quantum Hall states, you can clearly see the anisotropic resistance.
现在做的那个东西，然后现在非常非常 hot， 就是哈佛一个大佬就搞了一帮人
I think
搞了一个
someone may want to mute the. Okay. All right. Yeah. So it's been observed in quantum Hall systems that the people clearly see the anisotropic resistance when you flow current in two orthogonal directions. And also it's been observed in high TC systems, and actually it's been invoked as something that's unique in high TC, maybe one mechanism to achieve high TC, right? The mechanism is actually that to introduce fluctuation in these stripe phases, and at some particular optimal fluctuation, you can get both a high pairing energy and also a high phase coherence energy scale in the system. And that can automatically explain the dome shape for superconductivity. Well, the system that we'll be talking about, I'll give a very brief introduction because Alan and G yesterday already talked about it. This system may have some similarity to a high TC system. And the system we'll be talking about is a heterobilayer of a TMD, tungsten selenide on tungsten sulfide, 0 degree or 60 degree aligned. And because of the 4% lattice mismatch, it automatically will produce a moiré pattern on the material, which the moiré period is about 8%. And because the moiré period is mainly determined by lattice mismatch, so it's actually it's quite insensitive to a small change in the twist angle. Okay. And there's Bragg reflection, and as a result, it forms flat bands in the system. And it's been shown by Alan and his collaborators in a work in 2018 that these isolated moiré bands can be, the low energy scale can be actually described by a Hubbard model with I think the good way to think about it is that there is a harmonic potential, harmonic-like potential at each of these moiré sites, which can trap electrons, and the electrons can tunnel between the sites, and they experience on-site Coulomb potential U as well. Well, so the energy scale for the tunneling, intersite tunneling is about 1 to 10 MeV, and the on-site Coulomb is about 100 MeV. And in addition to the on-site Coulomb, actually, this is the typical device structure that we investigate in our study, is that it's embedded, usually the heterostructure is embedded between two gates in the system with a hexagonal boron nitride gate dielectric. And so there is an extended Coulomb term that should be included in the Hubbard model. So it's called extended Hubbard model. And I just want to note that this potential term that describes the interaction between the electrons is actually geometry dependent. It depends on the distance between the gates. The d here is the distance from the top gate to the bottom gate. Okay, so I would like to argue that this actually is important for compressibility. It's an important factor to consider in compressibility measurement. And the gate-to-gate distance is typically 10 to 15 nanometer. Okay, and because of this extended range Coulomb interaction, as just described by Philip, that can actually drive the formation of Wigner crystallized states. And yesterday, G already talked about these different states that have been observed in this system. And it's also very recently studied by some theoretical works as well. And today, my focus is mainly on the stripe phases. Okay, and you can actually look at some of these charge order states from the pattern that we propose in this experiment. They break rotational symmetry, like the nu equal to 1/2 is like this, and nu equal to 2/5 of 3/5 is actually like this. It's like a dimer, a chain of electron dimers that aligned in a particular direction. And the formation of these stripe phases, actually, Liangfu considered a simple V1, V2, V3 model. And so basically, it's driven by competing nearest neighbor and extended range Coulomb interaction on the triangular lattice. So that's the underlying mechanism that's driving the formation of these stripe crystal phases. Okay, the technique that we will be using to probe the stripe phases is a polarization rotation imaging technique. Okay, and the idea is very simple. You shine linearly polarized light onto the sample. Say if the sample is a magnet or a stripe crystal or some other stripe phases, the light interact with the sample, you'll get a polarization rotation by a certain angle theta that is proportional to the order parameter, right? If it's a magnetic material, it's proportional to the magnetization. And if it's a stripe phase, it's proportional to the anisotropy of the optical conductivity. And, so I want to mention a few things about, how to enhance the detection sensitivity using this method. It's a polarization rotation spectroscopy. You can imagine the simplest way to do it is that I put a polarizer in the incident beam, to polarize it. And then after it rotates by an angle theta, then I put another polarizer, which is cross-polarized compared to the first polarizer. Then I will detect the leakage of the light intensity to the detector, right? And then you can calculate how much leakage that you have. It's proportional because the electric field is proportional to theta. The intensity that you detect is theta squared. And theta is already very small, so theta squared is even smaller. So that's not actually the best way to detect polarization rotation. And the way that we actually use is a simple trick is called a homodie mixing, which is instead to put the two polarizer exactly at 90 degrees to each other, you just rotate the second polarizer by an angle phi here. That is much bigger than the signal that you're going to detect, but still much smaller than 1 when the angle is measured in a radian. So because of this rotation here, basically there's a leakage of the incident light, and that will actually create a local oscillator that can interfere with the signal that you want to detect. So the contrast that you will obtain on the detector will be actually developing a interference term that is linearly proportional to the signal you want to detect rather than to the signal squared. And as a result, this can dramatically enhance the optical detection sensitivity of the system. So let's see how it works. For a simpler system, just a single layer of magnet. There are not many spins on this system, right? It's a single layer of spins. And when we say polarize the spin to all the up direction, in this case, you actually can clearly see a brighter contrast at the sample region, which is bounded by this dashed line here. And if you just polarize the magnet to the down direction, then you see actually a darker contrast compared to the background, which is expected. And actually, even for single layer spins, using this technique, we can achieve a 60% optical contrast, which you can really see by your naked eye, right? And we can also just do this image at a single shot with an exposure time of just 10 milliseconds. And as a result, we can actually really start taking images, taking videos actually of the spin dynamics of this a single layer magnet. For instance, here I show you a single layer magnet that's warmed up from 18K to 26K. The Curie temperature is about 22 Kelvin. And as we warm up the system, you can actually see that near the critical point, the magnetization starts to spontaneously fluctuate. And then if you warm up further, the fluctuation is gone. And if you park your temperature near the critical point, near the Curie temperature of the system, and you actually can see spontaneous fluctuation of the magnetization. And so this, you can from here compute the spin-spin correlation function from these images. But I just want to illustrate that this technique really works well in terms of enhancing the detection contrast. Okay. Next, we will just switch our sample to the stripe, to the sample to the moiré samples, supposedly having the stripe phases. And the idea is again just very simple, right? You just put your sample, and as long as the instant polarization is not accidentally aligned to the major or the minor axis of the stripe crystal phase, then you'll be able to get a polarization rotation, and the signal is actually a measure of the optical conductivity and isotropy of the system. And this work is, as I mentioned, mainly driven by these three people here. Okay, so let's take a look at the data, how the optical anisotropy or the rotation signal theta here depends on the filling factor of the system. So here I labeled, the dashed line label all the charge order states that happened. Sorry, not all, actually most of the charge order states that happened between filling factor 0 and 1. And the bottom panel here actually shows the exciton emission intensity. As mentioned yesterday, this actually is an indication of the insulating state in the system, but I will present you the compressibility data later that they are indeed the incompressible states at these peak positions. So the main thing I want to mention here is that indeed we see a pronounced peak at 1/2 filling, right? At filling factor equal to 1/2. We have a large rotation in the polarization. And there are two curves here. I don't want to really get into the details. They are basically the detection, the detected signal when we rotate the polarizer to a positive angle or negative angle compared to 90 degrees. So basically it's constructively interfere or destructively interfere with the signal we want to detect. That's why one curve goes down, the other curve goes up. And but any case, it just really shows that there's a doping filling factor dependent polarization rotation, and the peak is exactly at the position that we expect the stripe phases. And this could be the two charge patterns for the stripe phases in this particular case. Okay. Well, then we can actually do imaging of the whole stripe pattern. So for instance, this is a measurement at a particular point, right? We can also take an image here. This is an image of the signal at a specific incident polarization, right? Compared to the stripe axis, and at a particular filling equal to 1/2 here. So you can actually see that the polarization rotation signal vary across the sample. It's bigger here, but it's smaller there. And it can also change sign depending on the location. That already suggests actually that the stripe phases, they form domains. Okay, then the next we can do is actually, instead of rotating the sample, we rotate the incident polarization, but effectively it's still rotating the sample. And as a result, we can actually take an image of the polarization rotation signal theta at each instant polarization. And as a result, that will actually allow us to map out the major axis or the minor axis of these stripe phases. And these are the...
Do you mind if I ask a question, actually?
Sure.
So if you were to tune the density away and come back, do you see that the orientation is changing, or is it somehow fixed?
Yeah, actually, I'll come actually briefly mention that point. The short answer is that actually we don't see a change in the pattern as long as we fix at a low temperature. But when we do thermal cycle, the pattern can change. Yeah.
Thank you.
And I will also mention the role of strain in this type of measurements as well. Yeah. Just bear with me for a second then. What it shows here is actually the rotation signal at these 3 particular points as a function of the incident polarization, right? And you can actually see that the stripe phases really at different points, they orient, the major axis orient at different angles. And then we can obtain a map. Here, the brighter color here means, a larger stripe, larger rotation angle. And the direction of this line here actually illustrates the direction of the stripe that is determined from the incident polarization rotation measurement. And you can actually see that within the boundary of the sample, most of the region, we do see stripe phases, and some regions are brighter than the other, and the orientation also will change from one place to the other. And we can make up a histogram based on the data here. And this is actually a histogram of the major axis distribution of the stripe phases. And you can actually see that there are 2 peaks. They actually differ by 90 degrees, interestingly. And so probably we have both of these stripe phases in the system. And also what's interesting is actually that these 2 peaks align to the crystal axis of the moiré superlattice, which are these orange dashed lines here. But there's also another interesting observation is actually that these peaks do not happen at each of these orange lines here, right? It actually picks a particular to pick 2 particular directions to align to, and we think that actually that's influenced by the presence of strain in the crystal, which actually acts like a magnetic field for a ferromagnet that polarize the stripe phase to a particular direction, so that we can actually image. That can form a reasonably large domain for optical imaging. And about thermocycle, so we can actually do measurements, after each thermocycle as well. And this is before, this is just the data I've shown you. And after 1 thermocycle, we just warm up and come back down, and it's still at a filling factor equal to 1/2. And you can actually see that the pattern is changed, and even actually there are some regions that the stripe major axis is rotated by as much as 90 degrees. That's actually somewhat surprising. But when you make a distribution function again, still the major axis still prefer to align to just those 2 directions, the 30 and 120 degree direction. And again, I think this is related to the strain and being, the presence of strain pinning down the local domains for optical imaging.
Can I ask, are these insulating phases, or what?
It's exactly at 1/2 is an insulating phase. Yeah, it's an incompressible state. Yeah.
Thank you.
Yeah. So an interesting comparison is to really compare the polarization rotation signal with the penetration capacitance that can measure at the same time on this device. So what the penetration capacitance tells you is that each of the peak you observe here is in an incompressible state. So that it's basically, you sort of expect that you have a filling factor 1/2, you have a stripe crystal phase, a filling factor 2/5 and 3/5, you have another, 2 other stripe crystal phases. And this is the 1/3 and 2/3 Wigner crystal states. Okay, and with increasing temperature, the 2 measurements actually, agree with each other. With increasing temperature, this charge order states melt, and also the polarization rotation signal would just disappear. And what's interesting in this set of data by comparing penetration capacitance measurement and polarization rotation is actually that the polarization rotation peak is much, much broader compared to the penetration capacitance peak for the incompressible states. And what this means is actually that we still have a polarization rotation. The system still breaks rotational symmetry even in the compressible regions of the system. So that suggests that, in addition to the stripe crystal phases, we also have evidence for the symplectic and the nematic phases. And this is a phase diagram that we just measure as a function. So this is the polarization rotation angle, which is related to the optical conductivity and isotropy as a function of filling factor and temperature. And the dashed lines are the expected stripe crystal phases. And as I mentioned, the polarization rotation extends over a much broader range compared to the crystal states. And this is the picture that we have so far. The stripe phases is sort of driven by a parental stripe crystal state at filling factor equal to 1/2. And when you change the filling factor, it goes through a nematic phase or a smectic phase, and then to an intermediate strike crystal phase at 2/5 to 3/5. You can actually think of it as microdomain structures between 1/2 and 1/3. And then if you further change your filling factor, from 2/5 to 1/3, it goes to a Wigner crystal phase, and intermediate is still a nematic phase. Okay, so that's what we have for the stripe phases. Then the next topic that I will talk about, if I still have time, I will be briefly talking about the compressibility of these charge order states.
So you have 8 minutes, Kim.
How much time?
8 minutes.
8 minutes. Okay, so I will try to bring out the message here. So the usual way to measure the compressibility of 2D electron gas is to build a parallel plate capacitor. You have a gate, you have a dielectric, and you have a sample. Okay, and you measure the differential capacitance by applying an AC voltage. And using a simple circuit model, you can actually obtain that 1 over the measured capacitance is equal to 1 over the geometrical capacitance of this device plus 1 over the quantum capacitance of the sample. Okay, and the underlying assumption of this treatment is actually that you can separate the electrostatic potential of the device and the chemical potential of the sample that you apply. So you write down the voltage you apply, V, is equal to the electrostatic part plus the chemical potential part. And the chemical potential part is related to the sample, so this is microscopic. And the phi here is related to the device, which is macroscopic. Well, as I mentioned, the Coulomb interactions that drive these stripe crystal phases, as well as the charge order phases in this semiconductor moiré system, is actually described by a geometry-dependent Coulomb interaction term, like this here. And the D here in this Coulomb interaction is equal to the gate-to-gate distance. In our device, it's a dual gate device, so the sample is located in the middle of a nearly symmetric gate. And as a result, we cannot really actually separate the sample from the device, because a device defines the interaction between the electrons in the sample. So we should actually think of that, the whole device, as our sample. All right. So the right way to really think about it is to consider the total energy density of the device, U here, and the compressibility is just obtained by the dN dnu. And nu is the chemical potential of the entire device, which is actually related to the curvature of the total energy density. And that's the measured capacitance of the device. So the measured capacitance, our argument is that it should be related to the compressibility of it should be interpreted as the compressibility of the device. And we are not the only one to actually interpret this. And actually, this was first pointed out by Skinner and Shklovsky in a PRB paper in 2010, that in the low density limit, when the electron-electron average separation is larger compared to the sample to gate distance here, one should really think about the system as a whole system, that the gate and the sample as your whole sample. Okay, and what they have predicted actually that in this low density regime, there's a capacitance enhancement at low density, and usually an enhanced capacitance in this type of measurement would be interpreted as a negative compressibility of the sample, but we think that the right way to think about it is really the enhanced compressibility of the whole device. And the reason for in this particular case, the reason for enhanced capacitance is because you inject charge is like injecting dipoles in the system because of the image charge when the gates are so close to each other. And as a result, the charging energy is so much reduced and the capacitance will just increase. Right. And we are also very interested in this problem because I think this is very much related to compressibility of interlayer excitons in this system. Okay, so about moiré. Moiré, we usually have a moiré period about 10 nanometer. And what that means is actually that the average electron spacing is bigger than 10 nanometer, right? Especially at the fractional filling states. And the gate-to-gate distance, we can make to about 10 nanometer. And as a result, when your gate-to-gate distance is small, we almost are always in the low density regime that you cannot separate the sample from your device. The whole device is the sample. And for instance, a simple calculation done by my colleague by Elsa at Cornell is that, so the model is very simple, just a lattice electron gas model with no kinetic energy for the electron. And they form this charge order states as I described. Then he went on to calculate the voltage you apply to the device or the chemical potential as a function of the filling factor on the, of this moiré superlattice. And this 1/3, 2/5, 1/2, they are the incompressible states. They are the, electron crystal states. And so the voltage, you just get a voltage jump here as expected because it's incompressible. But what's actually somewhat surprising is that the compressibility in the compressible region here, you can see that the voltage has no dispersion, in between the incompressible states. And you would actually just say that, this actually would give us an infinite compressibility or infinite capacitance that you would expect if you really have this perfect system that you can measure. Okay, so is that the case? Do we actually get a dramatically enhanced compressibility? The answer is sort of yes or no. We do get an enhanced compressibility or enhanced capacitance in our measurement. So this is a measurement measuring the top gate capacitance in this dual gate device. And it's normalized to the geometrical capacitance of the top gate here. And at high doping density, where the moiré features are almost gone, it just goes to 1 here. But you can actually see that in filling factor between 0 and 1 and 1 and 2, the compressibility for the compressible regions, they are all bigger than 1 by as much as some places about 30%. Well, it's definitely not infinity, but actually in the literature, this is also not a small enhancement in the capacitance. Okay. And for this particular device, I want to mention that the gate-to-gate separation is about 2 times of the moiré period. Okay, and we also have actually checked how this measurement depends on when we change the ratio of the gate-to-gate distance to the moiré period. And so this is showing, d over the moiré period to be 2. This is d over moiré period to be 3, the blue line. And actually, when you increase the gate-to-gate distance, you will see that the capacitance, this is a penetration capacitance measurement, which is actually, you can relate this by, you can convert this to top gate capacitance for 1 minus this ratio. This should be CP, sorry, not CT. Just make this slide too much in a hurry. And you can actually see that the enhancement in the top gate capacitance actually decreases when you increase the gate-to-gate distance. Okay, I will just skip that. You can also convert the charge density in the device as a function of back gate voltage that actually helps us to calibrate the capacitance mesh value that we measure to the moiré density. This is filling factor equal to 1, and you can see a gap. And certainly, you actually see a gap in the voltage, but you actually do not see a step function, just like for a perfect crystal. And to explain the discrepancy between this measurement and the expectation for a simple perfect crystal, White actually introduced a disorder into the system. We still have a moiré lattice, but there, on top of the moiré lattice, he included a smooth variation in the potential, in the moiré potential. That's a random potential. And so at the compressible region, you can actually see that depending on whether the system is at the potential minimum or maximum, and they force into phase mixing of this different local crystal states. And by just including a small amount of disorder in the system, actually a tiny amount compared to the total moiré potential depth. So this is the total disorder potential depth. By just including a small amount compared to the moiré potential depth, you can dramatically reduce the measured capacitance from infinity to a finite number at the compressible regions. And that sort of agrees reasonably well with the experiment. I stopped the graph here at filling factor 0.35 because the calculation is still ongoing. Well, finally, to just really show that this is really related to charge order, we perform a temperature dependence measurement. And you can actually see that with increasing temperature, the capacitance enhancement finally disappears. And we can actually plot the capacitance as specific filling factor as a function of temperature. And for the commensurate filling factors like 1/3 and 1/2, you expect the crystal states with decreasing temperature below the TC, the melting temperature of the electron crystals, the capacitance decreases because it goes to a incompressible state as expected. But at the compressible region, like in a filling factor 0.42 is an incommensurate filling factor, the capacitance actually increases when you go below the charge order states. So the capacitance enhancement here is we think is really related to this charge order formation in the system. And I don't need to really get to here. And with this, I just conclude that I hope I have convinced you that we have seen stripe phases and also liquid crystals states. And we also have observed a charge order enhanced compressibility of the device, not the sample, right? And well, the device is the sample. And well, there are some interesting open questions. Can we image stripe fluctuations like what we have done for the spin system? And can we actually include more stronger tunneling between the sides to really increase the bandwidth of the system and introduce some quantum effects? Can we continuously tune the bandwidth of the system to induce the quantum melting of the Wigner crystals at a specific filling factor? Those are the interesting questions that we would like to pursue in the future. And with this, I thank you for your attention.
Thank you very much, Kin-Fai, for the very nice talk. So we have some questions already. Shahal? Shahal, we don't hear you.
No, I didn't have a question. Sorry.
You didn't. Okay, sorry. Then, Kim?
Hi, Fai.
Hello. Nice to meet you. Yeah.
I know. So the transition temperature into the nematic phase that you optically detect at half, like filling half in your dome, right? So the dashed line, the tip of the dashed line, how does that compare to where you first detect the stripe phase? I'm asking whether there is a separation in TC between the nematic and stripe.
Oh, you mean whether here there could be some extra nematic phase?
Yeah, happening? whether because like in principle, right?
But we do not have enough sensitivity to detect that. So this is a relatively rough phase diagram, and we don't have enough sensitivity to combine, compressibility measurement to say that whether it's still incompressible or compressible, and then still see a remnant rotation signal. And one of the complication is related to the presence of strain in the system. So that is basically like if you apply a magnetic field to your ferromagnet, the transition sort of broadened, right? So this is the case also for this case that you have a strain. So the transition is broadened, so that actually complicates the matter.
But if there is a separation, that would be the fluctuating stripe that you are looking for.
Actually, if we can reduce the strain of the system, then maybe we can actually image the stripe fluctuation like we have done for the spins. And actually for the spins, if we just apply a small magnetic field and all the fluctuations are gone, right, as expected. So this is should be the same for the stripe as well.
All right.
So the spin fluctuations were measured on a 2D magnetic material, I presume, using Kerr spectroscopy, or?
It's exactly the same. This is actually Kerr spectroscopy.
So I was wondering actually, what was your detuning from the excitonic resonances when you were measuring the polarization rotation? I mean, were you detuned far out? I mean, because you mentioned that you could imagine looking at the fluctuations at around the critical.
So we actually choose specific wavelengths, right, to enhance the signal. And we compare the excitonic resonance, and basically the signal is the strongest, slightly red detuned or blue detuned from the excitonic. And I actually don't have the data here, but that's the answer.
Okay, thanks. Joy?
Hi, Professor Mak, could you please explain why the polarization rotation signal is related to the orientation of the stripe phases?
So for a particular, maybe this is the better picture to, so for a particular orientation of the sample, right, you have an instant polarization, this orange line here with respect to, the angle is with respect to some, major axis or minor axis of the stripe phase, right? And so the rotation angle here depends on the orientation of these samples compared to the instant polarization, right? For instance, if the instant polarization exactly aligned with the minor axis, like in this case here, you just get zero rotation, right? And as well as the polarization aligned to this direction. So if we rotate the sample, then we can actually map out the major and minor axis of the stripe phases. But in reality, it's too hard to rotate the sample. So what we do is to really rotate the incident polarization.
Thank you.
Philip, Kim?
Yeah, it's beautiful data, Fai.
Thank you.
I have the questions on the second part, this capacitance data. So when sample becomes incompressible, basically, in a sense, in terms of measurement, the resistance becomes large, and there might be some of the RC time constant maybe comes in, then you have to carefully kind of separate from this RC, right? Was that how insulating the sample can be, that especially in the low temperature when you get into the...
So that's why we actually limit our measurement to about 10K, not lower. Yeah. And the reason is that when you measure the resistive channel at the same time, the resistive channel would just shoot up significantly.
Yeah.
So we want to just keep into the regime that the resistive channel signal is negligible compared to the capacitive channel. So that's why we cannot really measure down to even lower temperature when the sample becomes really resistant.
Even say in this temperature, could it be this oscillation is in fact the signatures of coming from the resistance oscillation rather than capacitance, the quantum capacitance part?
We also have tested the frequency dependence. So it looks like it's a capacitive signal, everything. Yeah.
Okay. Good.
So we have to keep at a pretty low frequency and also a reasonably high temperature so that the resistance of the sample do not play an important role. Yeah, I think we have checked that. Yeah.
Great. Thanks.
Okay. Now, Phillips.
Right. So you're still seeing this negative compressibility that you attribute now to the whole sample.
Yeah. If you really insist to separate it, then it's a negative compressibility of the sample.
Okay. So, I mean, excuse me, of the device. It's not
the compressibility of the device is enhanced compared to the geometrical value. But if you insist to separate, to do a simple circuit model to separate this, you can only enhance compared to the measured capacitance can be bigger than the geometrical capacitance only if the sample compressibility is negative.
I see. Okay. Okay. So it's still the same problem is rearing its head here as well as in Pablo's data.
I'm actually not entirely sure about the gate-to-gate distance in Pablo's data. And also, also this interpretation really relies on the extended range interaction at fractional filling, because the extended range interaction is a geometry dependent, but the on-site interaction is geometry independent. For the integer filling states, we do not need to worry about this. I think we can just use this a conventional treatment.
Right.
I think it's a little bit misleading to call it compressibility of the whole sample. Capacitance of the whole sample is a better word, and so it's confusing when you say this.
Okay. You are the expert on this, and so I should call this capacitance of the whole sample.
You mean of the whole device?
Device.
Yes.
Device.
Okay. The sample is not the issue.
Yeah.
Okay. So there's one last question from Ziyu. How?
Yes. So you may have mentioned this, but is it possible to do a transport to study these charge orders?
It's possible, yeah. And when you get actually good enough contacts, it's possible. And we are making pretty good progress on that direction recently, but yeah, we still need to do more work on that. Yeah, it is possible.
I see. Thanks.
Okay, so with that, I suggest we thank Fai again and move on to the next question, next presentation.